Hi, hello. In this video, we are going to learn about correlation and regression. Correlation and regression is all about understanding the form of relationship and strength of relationship that may exist between two continuous variables. In fact, correlation and regression are a type of hypothesis testing, which will test whether a relationship exists between the two variable or not, right? Let us understand the correlation and regression in this video. So these are the modules, the topics we are going to learn here: correlation and regression analysis, and then the terms used in correlation and regression, and then we'll also see a case study. So regression is about, is actually a tool that will help us to quantify the form of relationship and strength of relationship. If there are two variables x and y, when I plot them in a graph sheet, whether the curve is going to be linear or curvilinear, and how how strong is the relationship between x and y. When I change the x, what will happen to the y, and what is the influence of x variable on the y variable. So these are all the questions we will be able to get answered by doing correlation and regression analysis. First, let us start with correlation analysis. So correlation is a measure of linear relationship between two continuous variables. So correlation will answer the question whether a linear relationship exists between the two variable or not, right? And see here, this is a scatter diagram I'm showing in the slide. The x-axis represents the x variable, and we are going to call x variable as the predictor variable, and the y-axis represents the y variable. We call y variable as the response variable. And for different values of x variable, the observed values of y variable are plotted in the graph, right? And then after plotting all the y values corresponding to the different x values, and I am able to see the points forming in a perfect straight line. That means there is a correlation between x variable and y variable, and the nature of correlation is positive. I call this correlation as positive because increase in the x variable has caused increase in the y variable. So the correlation is considered positive correlation. And moreover, the correlation is considered strong correlation. You know why it is strong correlation? Look at the way the points align themselves along a perfect straight line. Whenever you notice the points falling along a perfect straight line, and you can call it a perfect linearity, or you can call the relationship as strong correlation. And now moving on to, so this we understood strong positive correlation. Moving on to another example. Here also the points are falling along the perfect straight line, perfect linearity. So once again, I call it strong correlation. However, here the increase in the x variable has caused the y variable to decrease. And so the relationship is considered strong negative relationship. And in the third case, there is an x variable as well as a y variable. Here, I couldn't notice there is any linearity or any kind of shape getting formed. The points are completely scattered. That means I'll conclude that there is no correlation between x variable and y variable. That means your y doesn't depend on x. If y doesn't depend on x, why do you want to optimize the x variable? But here, the y depends on x. That means when you now control the x, you will be able to control the y. That means here, when you control the x, you will be able to control the y. In the first case, increasing the x will allow you to increase the y. In the second case, increasing the x will allow you to decrease the y. That means you have found the control knob for your y variable. You know what is the control knob? The x variable is the control knob. However, when your scatter diagram is like this, then you have not found the control knob here, because x is not going to control your y variable. Hope the picture, nothing but the scatter diagram has helped you to understand the form of the relationship, right? And also the strength of the relationship. Perfect linear means strength is strong. And if you see some ups and downs here in between, the strength is weak or moderate. And in order to do this predictions correctly, and we can also think of using this formula, which is called Pearson correlation coefficient, where R equal to 1 by n minus 1 summation of x minus x bar divided by sx into y minus y bar by sy. Here n is the number of data you have, and x bar is the average of the x value, sx is the standard deviation of x value. Similarly, y bar is average of the y value, Sy is the standard deviation of the y value. Xi and Yy are the individual x and y values. And now when you calculate the R, your R will always fall between -1 and +1. Right? It can assume any value between -1 and +1. If it becomes +1, then you can understand the relationship is strong positive. If it becomes -1, then the relationship is strong negative. Or you can also call the relationship as perfect whenever the Pearson correlation coefficient approaches 1. When the same Pearson correlation coefficient approaches 0, you can conclude there is no correlation between x and y. That means looking at the R value using this formula, you can comment on the strength of relationship. You don't have to look at this scatter diagram, even without the scatter diagram. But always having a scatter diagram is a good idea. But even if you do not have, the R value can still help you to conclude correctly, right? So 0 to R value ranging from 0 to 0.4 is called weak correlation. 0.4 to 0.7 is called moderate correlation. 0.7 to 1 is called strong correlation. You have 0 to 1 for the positive correlation. You have 0 to -1 for the negative correlation. And see here, I am also showing a graph here, which is nothing but a scatter diagram, one of the 7 basic QC tool. The x-axis represented by the calories consumed, or calories consumed is represented along x-axis. Please note, calorie consumption is a continuous variable. We call it predictor here, the x variable here. And depending on the calories you consume, your weight gain happens. Weight gain will generally increase when you consume more calories. Weight gain is the y variable here. We call it the response variable. Calorie consumption is the x variable. See, I keep on increasing the calories, and see here, my weight also keep on increasing. My weight gain is also keep on increasing. And the points are plotted here. Now the blue color points are the real experimental values. Look at the way the blue color experimental values are falling. It falls almost along a straight line, but not a perfect straight line. So I won't say the relationship is perfect linear relationship, but definitely it is a strong linear relationship, because these blue color dots are almost close to the red color line, where we call this line as regression line, and we will talk about the regression line in the upcoming lesson. However, now when the points are too close to the regression line, you can conclude your correlation is strong. Since the line is going upward continuously, you can also conclude the correlation is positive correlation. And see here this example. And if you look at this graph, the points are continuously moving upward and the points are close to the regression line. And that means it is strong positive, and that is confirmed with the higher R value. And this is strong negative. Points are close to the line. However, the points are moving downward as I increase the X. And that is again confirmed with the Pearson correlation coefficient. This is strong positive and this is strong negative. And here, this I would say weak positive, because the points are far away. You can see the points are far away from the regression line. And this is weak negative. So weak positive and weak negative correlation. And the third one, and now I cannot make any conclusion because the points are completely scattered. That means I am not able to comment what happens to y when I change the x. That means x is not a variable which can control your y. So under such situation, I will say there is no correlation. But look at another graph. Here also there is no straight line. I cannot see a straight line, but I can see a curve here. It is a parabolic curve. So the first case, there is no correlation as well as there is no relationship. But in the second case, there is no linearity, so I call it no correlation. However, still there is some other relationship, which is a quadratic relationship, which is a parabolic relationship here. So I call it parabolic relationship, but no correlation. So what do we understand here? Correlation means linearity. No correlation means no linear relationship. But even in the absence of linear relationship, there can be a quadratic relationship, right? And that is what we call it parabolic relationship. Hope the correlation is properly understood. We'll also see a case study after understanding the basics of the regression. So what is regression analysis? Regression analysis is nothing but framing the mathematical equation of the regression line. Framing the mathematical equation of the line, showing the relationship between predictor variable and the response variable. And regression also can help you to understand the direction of relationship, whether the relationship is positive between x and y, and the size of the relationship, And regression will also tell about the statistical significance. You know, statistical significance is nothing but the p-value. If you make any conclusion always with some data, and your conclusion will be perfectly correct whenever the p-value is very low. So regression analysis comes with a p-value also. And then regression can be used to predict the future future observation. And that means regression can also be used as a prediction model. You have set of experimental values of x as well as y. If you wanted to know the value of y for a new value of x, then when you have a prediction model, then you can use the equation as a prediction model, regression equation as a prediction model. But there are certain conditions, only when those conditions are satisfied, you can use the regression model as a prediction model, otherwise not. And then the principle of least square, because when we are using the statistics, when we are framing the regression equation, we follow certain assumption, right? And one of the assumption is, the deviation from the line, should be minimum. And so that is called the principle of least square. That also we'll see in the upcoming slides. So terms used in regression analysis, regression model. There are different regression model exist: linear, quadratic, cubic, and so on. We'll see them. And then there is something called regression equation, nothing but the mathematical equation showing the relationship between x variable and the y variable. And then regression coefficient. In your regression equation itself, you will have y variable on one side and all the x variables on the other side. And each x variable will be, having a coefficient. That is what we are going to call it as regression coefficient. And then there is residual, right? And all these things, these are the terminology associated with regression. We'll understand them. See here, I have a scatter diagram. I have scatter diagrams on the left side. The first scatter diagram says that the relationship is almost linear. When I look at the scatter diagram, and if my scatter diagram indicates the form is along a straight line, then I will now go for a linear regression. When I go for a linear regression, my equation will be like this: y equal to ax plus b, or otherwise you can call it y equal to mx plus c, a standard format, right? You can use any symbol, a and b or m and c. When I say y equal to mx plus c, that's the simple linear regression. And also I can have multiple linear regression where the number of x factors will be more than one. See here, there are two x factors: y equal to ax1 plus bx2 plus c, and this is called a multiple linear regression. And now you can consider this regression as regression equation of model order 1. Why do I call it model order 1? Model order 1, because all the x terms are maximum having the power of 1. You will not have any x square, x cube involved in your regression equation, and that's called model order 1. Now moving on to model order 2. When should I go for a model order 2? When should I include the terms x square in my regression equation? When your scatter diagram is showing like this. When the moment you understand the relationship between x and y is curvilinear, maybe quadratic or some other nature, accordingly you can proceed with the model orders. And since this is quadratic, that means like a parabola, you can go for a second degree equation. The second degree equation will have x square involved. So y equal to x square plus bx plus c. That means there are 3 constants involved. And now that means the model order is 2. And see here, when you go to the third option, you can see the nature of the curve in the scatter diagram. The curve is going up, coming down, and again going up. If this kind of ups and downs you are using, you can understand the relationship is cubic in nature. And now you can go for a third degree equation: y equal to x cube plus bx squared plus cx plus d. In order to derive these kind of cubical equation, you must at least conduct 4 experiments, because there are 4 constants involved. And here for quadratic equation, there are 3 constants involved. So you must at least conduct 3 experiments to frame this equation. However, for simple linear regression, there are only 2 constants involved. Just 2 experiments are good enough to frame the equation. That means if you have any 2 points on this blue color line, then the line can be drawn. However, for a parabolic or this kind of quadratic equation, you not only require the end points, you also require the middle point. However, for a cubic equation, you require this point, and as well as these 2 points. And this is what we see here in the form of constants. Probably we'll understand and talk about all these constant terms and then experimentation probably at a higher level. But I hope now you got a clear idea about what is linear regression, quadratic regression, and cubic regression. Linear regression means regression equation will only have x terms. Quadratic regression means your regression equation will have x square term also involved in addition to the x terms. Cubic regression means your regression equation will have x cube involved in addition to x squared and x. And now you see here there is a regression equation here. And this regression equation again talks about two variable, calories consumed and then weight gain. As the calories consumption is increasing, the weight gain is also found to increase. And now this is the regression equation. See here, weight gain, the y variable is equal to a constant term minus 754.6 plus 0.4631 calories consumed. The calorie consumed is the x variable and this weight gain is the y variable. You can represent this in the form of y equal to mx plus c. Now m is the regression coefficient. This m is nothing but 0.4631. And you can easily find out this m value. This m value is nothing but the slope of this particular straight line. The slope of this particular straight line. So how to find out the slope of this particular straight line? Measure this angle the regression line is making with the x-axis, right? And you can measure it as theta. Let me also draw it for you. Let me take the pen and see here. Draw a horizontal and then measure this angle theta. And now go for tan theta, right? Tan theta. Tangent of theta. Now m equal to tan theta will give you this 0.4631. Another way of finding out is after drawing the horizontal, draw a vertical. Now measure the length of the vertical as well as the length of the horizontal. The length of the horizontal is considered to be del x. The length of the vertical is considered to be del y. Now you can find out the same m using another method, m equal to del y divided by del x. That means del y is nothing but the opposite side. Del x is nothing but adjacent side. So that means once again you are finding out the tan theta, right? So m is found to be 0.4631 in this method. And then c can be found by extending your regression line, by extending your regression line. And see here, once again, I'm taking my pen. I extend this. Now you can understand this line is crossing your y-axis at this point. At this point below the origin. And that's why, you have a negative value here, minus 754.6. So minus 754.6 is nothing but the y-intercept, nothing but the point at which your regression line is crossing the y-axis. So once you know the constant minus 754.6 and 0.4631, you can frame this complete regression equation. All right. So regression can indicate the direction and size of the relationship. How? Look at the regression coefficient. Since the sign is positive, you can understand the relationship between x and y is positive. That is what you are noticing here. As the x increases, y also increases. And regression can not only indicate the size, but also the size of relationship. You know what is the size of relationship? 0.4631 gives you an idea. What idea it is? When I increase the x variable by 1 unit, y variable will increase by 0.4631 unit. That means this regression coefficient can help you understand the direction as well as the size. The sign of the coefficient indicate the direction. The coefficient value represents the change in the response variable you may observe by changing the x variable by 1 unit. So in order to better understand, I have another slide here. See here, this equation is a simple equation passing through the origin only. If it passes through the origin, then the constant term will be y-intercept will be 0. So the equation is y equal to x. It simply means when I increase x by 1 unit, y increase by 1 unit. When I increase x by 1 more unit, y again increases by 1 more unit. That one is nothing but regression coefficient. So regression coefficient is helping you to understand how the y variable will change when you increase the x variable by 1 unit. But coming to this particular equation graph, see here, again it is passing through the origin. Increasing the x by 1 unit increases the y by 2 unit. That means the equation here is y equal to 2x. Here it is y equal to x. Here it is y equal to 2x. That is how we commented here also. Y equal to 0.631x. That means increasing x by 1 unit will increase the y by 0.4631 unit. So this is how the regression coefficient is helping you. Residual. Look here, this I'm showing a scatter diagram in a magnified manner, and the regression line is here, the blue color one. However, the observed points, the experimental values of y are now slightly above and below. Though the points are slightly above and below, we are interested in finding out the equation of the blue color line only. And this blue color line is used to represent the relationship between x variable and y variable. And so there is a residual involved. You know what is residual? Nothing but the deviation, nothing but the error. The observed value is 380, but we simply assume that the point is lying on the blue color line to find out the equation of the blue color line. So we pull down this point and we make it lie on the blue color line. So the difference between the observed value and the fitted value, this is called fitted value, is called residual. Say for example, the first point, the observed value or the actual value is 380. It is pulled down, and now the fitted value is 350. Now you know the difference. The difference is 30. This 30 is called the residual. Similarly, the residual can be negative. These points you have to pull up. So these residual, if there is more residual involved while framing the regression equation, your regression equation cannot speak the reality, and then your predictions and conclusions based on your regression analysis may go wrong. So what is the idea is, the idea is when you are writing the regression equation, make sure the residual involved is minimum. That is why we draw the line carefully in such a way that the distance of the line to the point is close, very close, and or otherwise it's small enough so that the residual can be low. And this idea is called the principle of least square, because the residual is there on the positive side as well as on the negative side. Positive side also is error, negative side also error. The total error should be 0. So we have to square the errors, and then the sum of the squared value should be 0. This is what we call it principle of least squares, right? And now let us do the correlation as well as the regression with a small case study. See here, a person is studied for his weight gain for different values of calorie consumption. So he consumes 1500 calories and he is found to stay at the same weight. Suppose he increases the calories, then his weight is also found to increase 200 gram, 900 gram, and something like that. And now I really wanted to understand whether the calorie consumption has an impact on the weight gain. Now the null hypothesis is calorie consumption has no impact on the weight gain, right? That is the null hypothesis. And what is the alternate hypothesis? Calorie consumption has an impact on the weight gain. Now let us do a correlation study. With the set of x value and y value, I'll go for the Pearson correlation coefficient. We know the formula, and the Pearson correlation coefficient is found to be 0.97. 0.97 is close to 1. That means the relationship is almost perfect linearity. I will say very strong relationship. Very strong relationship means yes, the x variable has got an impact on the y variable. And and you can also go one step further. You square the r value, then it becomes coefficient of determination, r square. When I square r square, 0.97 will become 0.94. It simply means 94% of the changes you have observed in the y variable are due to the changes you have made in the x variable. That means the calorie consumption has 94% influence on the weight gain as far as the particular individual is concerned. That means the calorie consumption is the single root cause of the problem weight gain for that particular individual. And this is what you are seeing in the form of the graph also, that is the scatter diagram. You see all the points are close to each other, and see here your R square is 94%. This is a Minitab report, and you can feed the data to generate similar report. And now for the same problem, let us go for the regression equation. The same set of data when fed, the regression equation is found to be weight gain equal to minus 754.6 plus 0.4631 calorie consumed. We have clearly discussed about the meaning of 0.4631 as well as minus 754. Minus 754 is the y-intercept, 0.4631 is the slope of the line. And see here, your predictions are confirmed with the lower p-value. And any regression analysis, whenever you do, any regression equation, whenever you derive, it will come with the model summary. And the model summary here will have an S value, will have an R square. These two are very important. S is a measure of the residual. If the S is more, that means the residual will be more. If the residual is more, probably your predictions will not be accurate. And so we always aim for a lower S value. And now R square should be higher. R square is a measure of the strength of the relationship, influence of the relationship. You remember when we squared the R value, we got 94%. That is what is appearing here, 93.53, right? So we need a higher R square value. R square value above 80% is considered to be a good regression equation. All right. So what is that we have learned in this lesson? Regression is a technique to generate a mathematical equation describing the relationship between the x variable and the y variable. And what is important here is both x variable and y variable should be of continuous variable. A Six Sigma team can make use of the regression equation to investigate the suspected relationship between x variable and y variable. And if the regression equation is developed with the lower s value, and then if the R square values are good, you can use the regression equation as a prediction model, right? You don't have to do more experimentation. Rather, you can use your regression equation to predict the new observation. And regression result can indicate the direction, size, as well as statistical significance of the relationship. The regression coefficient can help you to estimate the change in the y variable for every unit increase in the x variable. You increase the x by 1 unit, what will happen to the y variable? The regression coefficient will answer. So regression can be used to model linear relationship, quadratic relationship, cubic relationship, or even higher order relationship. But the initial clue comes from the scatter diagram. If the scatter diagram reveals the relationship is linear, go for a linear model. If the scatter diagram suggests the relationship is parabolic, then go for a quadratic model. If it is cubic, go for a cubic relationship. Hope you have understood the correlation and regression tools very effectively. And I'll see you again in the next video. Thank you for watching.